Everyone is doing fine with the quarantine, like self-isolation and everything. And I guess everyone is taking the meeting from their home, and everyone is safe and fine. And with that, we will start the discussion. So I'm going to present you a topic. Is called pose estimation with limited data. So what I will do is I will do a state-of-the-art analysis of three of the papers that I've selected among many others. And then I will discuss how my research probably can be planned around that, and what will be the problem space for my research in this particular domain. Okay, so Fangshus wants me to make it full screen. Okay, let me see. How can I do that? Okay, is that okay?
Yeah.
Great. Now, all right, so the goal of our presentation would be to understand the state of the art, as I told, of pose estimation, but with limited data. I will go into the data in the next slide, but what kind of data we'll use. But just to be a bit more narrowed down, we will mostly use IMU, that is the inertial measurement units for the analysis. By inertial measurement units, it means like sensors attached to, that can be attached to the body or can be used individually also. And it consists mostly of three forms of sensors, that are accelerometer, magnetometer, and a gyroscope. However, and that we'll discuss the rest of the things a bit later. And we will see the extension, how this can be extended to our research. And after that, we'll also see other possible applications that can be used on this particular domain, apart from the application on which I will be targeting. We will start the discussion in the following line. We will discuss what is pose estimation, generally speaking. It's a very small slide. And then we will discuss the evolution over the research works which I have selected. This part, the background part, will be important because there are things which I did not have an idea about when I started the research. And I think that background, we'll just discuss briefly on those background. We'll cover those just for the sake of understanding the papers with a bit more clarity. And then I'll talk about the specific application to research on which I'll be working, and the possible research areas which we can explore while we do the same thing. And there is another factor, which is the collaborative learning, which I discussed with Sarunas last week, and we and I also talked with Krista regarding this, and we decided to brainstorm this after in the next phase of my research. And finally, I will talk about the other applications where this domain can be useful. You can stop me and ask me questions at any time of the presentation, because there are things probably which I am also learning, so your input will be of great value in that perspective. Okay, so what is pose estimation? In general, pose estimation is research as a computer vision problem where we have as an input an image or a video of a particular person or multiple persons, and in a certain posture, like for example, walking, running, and we are supposed to represent that posture in terms of key joints or key points in the body itself. So generally speaking, people who have already known pose estimation problem, probably they have known this as a from the perspective of computer vision. And in computer vision, we mostly have images and videos as input. But for if you see the slide, you can see that there is this other data part which is highlighted in red. So this is, I have added this part because we for this presentation, we are not really interested in the image and the video perspective. Of course, like there are very good works that are done with image and video, and most of them are done with image and video. But for our presentation, we will be concentrating on the IMU part of the data, and that's why the other data is highlighted in red. And if you can see from the image, then these are the key points which are represented in the human body, like arms, and these points can be joints, or sometimes it is also denoted as like muscles in some complicated procedures, but we are not going to discuss that. And if you see that in this particular human who is walking, we have represented the pose of the human in terms of the key point. One thing to understand is this is not identifying a particular person, but it is about identifying the posture or the pose of the person in terms of generic key points of the joint. I was discussing with my friend Vangjush yesterday, and he added an important point which I must mention, that pose estimation can also be thought as a compression process of data, because it is essentially representing the whole human figure by compressing it into certain key points and joints. So in that perspective is also we can explore that perspective also, but for this presentation I will not explore that, but that's an important point to mention. So, what are the possible research areas and application domains which is touched by the pose estimation? So, as we can see, like computer vision, deep learning, mathematics, physics, graphics, animation, human analysis are mostly the technical or the research part of it. And apart from in the application part, it can be used for motion modeling. It can be used in a lot of use cases in sports. These two are the most common. Apart from that, health and well-being is also somewhere this particular techniques are used. For example, gait analysis, when we have to understand the posture of a leg to identifying injuries and stuff like that. And some of the perspective directly draws parallel from graphics and graphics to animation. Like there are some techniques which directly models a particular animated body in terms of human motion, and this is a common use case, but we are not going to explore that in our presentation. So now I will talk about three of the papers which I have selected. These three papers that I selected mostly like intertwines a story together of how the pose estimation is done with IMU data. So the first one, and these three works I've selected because I believe that the first work, the pose estimation from videos and IMUs, is the most cited work in this particular domain when it comes to pose estimation with limited data or inertial measurement unit data. So when I say IMU, you can just think of accelerometer, gyroscope, magnetometer, and stuff like that. So this is the paper that is done by a group of researchers from Germany. And then we have an extension of the same work, which is again done by the same people, where they do not use video also, they just use IMU for pose estimation. And finally, another work which is not by the same researchers, but it is actually let's say influenced by the previous work. The sparse inertial poser is a deep inertial poser, while they have used deep learning to do pose estimation only with IMU data. So in a way, it also shows the evolution of how the thing works. So previously, or these papers, the timeline of the papers is like 2016, 2017, and 2019 or 2018. I forgot the last one. So if you see from the perspective, like you can understand that deep inertial poser also marks the beginning of, let's say, usage of deep learning techniques directly with pose estimation with IMU. This is important because deep learning, there are many deep learning techniques which has been used for computer vision problem of pose estimation, but with IMU, this was one of the very first works that I have like found so far. So three papers are kind of fundamental to begin with, and that's why I selected these three to present my work. Now we will discuss about like the background, and the background is important because it is something that is central for the mathematics of all the paper. We don't need to understand all the mathematics for the presentation, so I will just present things which are very, let's say, basic to understand. Not very basic, but at least important to understand, to know the basic formulations of how the paper works, or how the architectures of the papers work. And in general, now I will concentrate on like model based pose estimation. So when I say model based pose estimation, one thing is important to understand. It Model based pose estimation aims at recovering the human motion or a human pose from a 3D model representation of human body. And when it says model based, I mean the human model, the human 3D human model representation. It is not about let's say mathematical model or probabilistic model, etc. Of course, this 3D human model is like, let's say represented as in mathematical notations and mathematical in vector notations for ease of computations. But for this heading, it can be like, I was also kind of misidentified this as like some probabilistic model of pose estimation, but it's not that. It's just like the 3D human model, that what it means. So the 3D model representation, yeah. And now when we have said that, so to represent a 3D model, we need some kind of parametrization, which we call kinematic parametrization. Then once we have the kinematic parametrization, we can create a model. And once we have created the model in terms of some mathematical equations and vectors, we can optimize over those equations and models to create the perfect pose. So essentially we have to find representation of poses, so that in vector terms, so that we can optimize over those to find the ideal pose. That's more or less the objective of the whole procedure. And now I will drop into a bit more detail of the kinematic parameterization part, and we will see what are the let's say concepts, or what are the uh, techniques or tools that are required for parametrizing the human body in terms of a kinematic chain. Yeah, so as we know that human motion is like mostly articulated, that is it has a natural perspective to it, and it also draws parallel from robotics. And that is why, for accurately modeling human motion, we can think it as in terms of we have couple of segments in our body. So if we see the image to the right, on the left half we see a human image, on the right half we see, let's say, the robotic representation of the image. And we can see that the arm can be modeled as a segment, the lower arm can be modeled as another segment, with a joint in between them, which connects these two segments. So to determine a pose, we must find the appropriate parameterization for the human motion in terms of these segments and joints. And there are a couple of requirements for good parameterization. We need, of course, like any other technique, we need minimum number of parameters to represent this thing. And these parameters must be such that it can represent a human motion naturally. And this term is most of you probably would agree on this term, that we need the parameters so that there is easy computation of derivatives for the segment positions and the orientations with respect to the parameters itself. And this is because we need if we have easy calculation of derivatives, it makes it very easy to optimize with any kind of descent mechanism or any other optimization technique which require the derivatives. And finally, this is an important part. We must need rules, simple rules, so that we can concatenate the motion together. I don't know how to remove this thing. Anyone know? Because I think this is obscuring the image, right? Uh,
I don't know, but I think if you just don't move the mouse too much, it will disappear.
yeah, but I wanted to like
Yeah.
I'll just try to I wanted to use the mouse so that I can like point at the parts. But anyway, so if you see the image in the bottom, you can see that there are two segments connected with joints by a joint. Now we can think this as our arm, while the right hand side segment represent the lower part of the arm, and the left hand side segment represent the upper part of the arm. Now, when we move our arm a bit up, then there is an angle that is formed about the joint. And if we see the image, we can clearly see that this whole movement of the arm is an effect of moving both the upper and the lower parts, because both of them move together with respect to the spatial frame, which I cannot point, but anyways I can, which respect to the spatial frame where the arm is placed. So there is an angle theta 1 which is formed with the spatial frame by the upper arm. There is an angle theta 2 also, which is formed by the body frame, which is attached to the body. And this theta 1 plus theta 2 form the angle of the upper arm uh, with the spatial frame, which is here. Sorry, I was like, the figure is kind of obscured. So but anyways, I hope you got what I meant to say. So for parameterization requirement, we need such simple rules, like good parameters with which we can model the motion effectively by simple rules. And this representation is essentially called a kinematic chain. So what we have learned so far is we need good parameters to represent poses, and those poses can be modeled as a kinematic chain. Now we will come down into a bit. Okay, let's there is sorry okay, so kinematic chain, as I was saying, so it encodes, I already told this in the previous slide, it encodes the motion of the body segment as motion of the previous segment in the chain. And that's what I was explaining, like this part of the body is affected by the movement of this part of the body. So it's like this part does not move independently, so there is a dependency between these two parts, and the parameters should be so designed that this dependence can be captured very easily. And there is obviously an angular motion about the joint. So this is what I was explaining. The motion of the lower arm is parameterized by the motion of the upper arm and a rotation about the elbow. I forgot that I put a slide just because that was not visible in the previous slide. anyways. All right, so our goal is to define human pose parameters in mathematical terms so that we can use that to model some okay, so there is a test written on top. Okay.
Oh, sorry, I thought I wrote on my screen. I just trying to figure out the options for.
No worries, but it's a good thing. You can probably
I will try to erase it. Just continue. So sorry, I thought it's my screen only.
No problem, no problem. So yeah, as I was saying, what we want to represent is we want to formulate the human pose in mathematical terms. That is called pose parameterization. And the pose parameterization is also, it can be called as a kinematic parameterization because we are using kinematic, let's say, chains and kinematic models that we use in robotics mostly. And for defining this kinematic chain, there are a couple of concepts that we will just briefly go through. If you have some detailed question, you can definitely like ask me, and I will try to answer those with the limited knowledge that I have right now. So the first thing is like rotation matrix. Then we will represent. Then we'll discuss about the axis angle representation of the rotation matrix, and then we will come back how we can form kinematic chain with these two concepts that we see before, and finally how the kinematic chain can be used for parameterizing human pose. So once we have the kinematic parameterization, we can create a model, and hence we can optimize the model. This is the meat that I'm trying to like push through. That in order to optimize, we need the representation of the human body in terms of mathematical model, and once we have the model, we can optimize. So I will come back to the rotation matrix. Rotation matrix is simply, so for example, let's have a look at the slide. So we have a spatial frame which is attached, which is not attached to anything, but that is the frame that you have in space. And when we want to represent any motion, we want to represent it in terms of the spatial frame. In addition to that, we have a frame called B, which is attached to the body. So once the body frame moves, there is a translation or a representation of that in the spatial frame also, and we need to capture that transformation in the spatial frame. So for example, if there is a point PB in the body frame, we can translate that point PB into the spatial frame as PS is equals to RSB into PB, and this RSB is the rotation matrix which tells you, or which denotes the transformation rule of transforming from the body frame to the spatial frame. So that's what a rotation matrix is. And now since a motion is considered not only of rotation but also a translation, because it's a rigid body motion, the human is not like just a fixed person who is just moving or rotating his arms and legs, but he or she also can move forward. So there is a translation that is involved. So that's why there is another additional factor called a TS, which represents the rotation as well as translation. And a rigid body motion is usually expressed as a factor of a rotation and a translation in this formulation. So that is what a rotation matrix is. Next is what we'll see is how the rotation matrix is represented in axis angle representation. So we can think it of in this way. So to model a human joint motion, it is if we can specify the axis of rotation of the joint, then we can just have like two parameters: the axis of rotation and the angle that with which it rotates around that particular axis theta. So if we have the theta and the axis omega, we can represent have an exponential formula for the rotation matrix. This is just a representation. R equals to exponential of theta multiplied by omega dash. So omega dash is the skew symmetric matrix of like omega. And one thing I should have mentioned, but I guess most of you probably have already assumed, that omega is like three axes, x, y, and z, because that's 3D motion. We consider 3D motion while we in this particular space. So this is a skew symmetric representation of omega, and it can be expressed as exponentiation of theta multiplied by omega dash. And why we use this particular form is because this has a closed form solution, which is called the Rodriguez formula. And once we have the closed form solution of this, if given theta, we can easily calculate the rotation matrix. And given the rotation matrix, we can also calculate the angle around which the joint rotates. So we know what is an axis angle representation now. Now we'll try to represent rigid body motion. That is, now we have considered for this slide only rotation. Next slide we will see rotation plus translation. So a rotation plus translation essentially is called a twist, and in 3D space it can be denoted as a factor of 6 coordinates, omega 1, omega 2, omega 3, representing the axis of the rotation, and v1, v2, v3 represent the spatial axis along which the body translates or transits. So a rigid body can be expressed as a factor of theta and omega again, and here this is the rotation factor, this is the translation factor, and this is 0 and 1 is added just so that we can make the matrix symmetric. And it can be represented again in exponential form as we have seen in the previous slide with theta omega, which is called theta and eta dash. Eta dash is a symmetric representation of theta, and this term is called the twist action. So it represents how much twist or how much rotation plus translation happens for the rigid body. And these forms again are just for ease of calculation. The prime thing of the discussion is that we can represent a human movement as a rotation plus translation or a twist in terms of 6 independent coordinates. We have discussed 6 degrees of freedom so far, and theta can be any other number of angles, which we'll discuss in the coming slides. And then again, just like we have defined omega 1, omega 2, omega 3 as skew-symmetric matrix, we can define eta dash also as a skew-symmetric matrix of eta, and given with the same notation and the translation coordinates v1, v2, and v3. Now, so now we have defined all the things that we need to define a kinematic chain. So I'll just remind you, we have defined rotation matrix, the axis angle representation of the rotation matrix, and this is required to define the kinematic chain, and the kinematic chain is required for parametrizing human pose in terms of vectors. So then again, coming back to the previous the image that I already have shown you. So a translation across a spatial body frame can be represented in the spatial frame with the rigid body motion parameter, if you remember, it was called G. So we can say the rigid body motion of this object, and in the body frame multiplied by the coordinate of the body frame gives us the coordinate in the spatial frame, and that's what we need to find. And this rigid body the rigid body motion of the whole body can be represented as individual components. G1 represents the upper and lower arm, rigid body matrices of the upper and the lower arm, and GSB0 just represents the transformation of the rest pose for the B to S. So what happens in practice is usually when there is a rest pose, this is the rest pose, and in this particular pose we know how to translate from B to S. This is just the initialization factor when you see it from a practical perspective. And once we know this initialization factor, after the rotation, concatenating the rigid body matrices G1 and G2 and the rest pose helps us to translate the coordinate a point from the coordinate frame of B to a coordinate frame of S. And again, this is just the rigid body notation, and we can just extend it to the axis angle representation. And once again, I remind you, the axis angle representation is important just for calculating the closed form, because we have a closed form solution for the same, and it can be easily used for computation. And a generalized kinematic map, which consists not on of 2 angles but of n angles, can be given as the notation that we see below. It's like the rest pose transformation multiplied by all the exponentiation of the skew-symmetric matrix of the twist parameters. Now we have defined all the things that we need to define a human pose. So there are many kind of like joints and poses which can be defined. So for example, when we consider the whole human body, we can call it the root joint. So the root joint is the same as a rigid body. So we define it in the same way as we define a rigid body motion, that is with 6 degrees of freedom, the rotation and the translation. And on top of that, if we have multiple angles, then we add 6 plus n. So that is the degree of freedom for the root joint. Similarly, there are different kind of joints which can be defined. which can be defined according to the diagram that you see. But the most common one in literature is a revolute joint and a root joint. Like a root joint is the whole rigid body. The revolute joint has only the ability to move across about an axis. So if we see the image below, this is a revolute joint. So it can just it cannot translate. It can just rotate across this particular hinge or this particular joint. So this is a revolute joint, and the advantage of having just a revolute joint and root joint is uh, we can, since it's the last, let's say the last leaf of a tree, in a way you can see, we can combine two revolute joints to form a saddle joint, or more than two like revolute joints to form a ball joint, and all the other formulations can be easily done with a revolute joint. So that's what we mostly use. The rigid body of the human rigid body can be considered as a root, and all the other joints can be considered as a revolute joints. So we can parametrize a human body, which is like why we were seeing all these things, as a factor of two like things. The first one is called eta, which is the twist parameter, and which is given by the axis of the rotation and the axis of the translation, and theta, which is a subset of all the angles of rotation that revolute that can occur in the human body. And if there are n angles, then we can have 6 plus n degrees of freedom for the whole defining the whole movement. So if you have any questions, you can ask me. That's okay. All right, so I will move to the next part. Now, once we have done the human, we can the parameters to define a human pose. We can now create. Yeah, sorry. Yeah.
I just raised the hand, so.
Okay. I did not see where there was a. I didn't see any notification. Sorry.
No, it's okay. No, when you were speaking about translation and rotation, I was thinking in back of my mind, how is there any possibility this could be done, could be reparameterized in the Fourier domain? Because that would like probably reduce the order of the modeling and probably, hopefully, faster computation.
I think you have a good point, because there is a possibility, and I have seen certain papers do that. I think at least one paper I've seen do that, but to be honest, I did not go into much detail, because when I was doing the research, that paper was not very recent. It was, I think, in 2008 or 9. So I assumed that the other things that has been done are, let's say, are better than the paper that I've seen in 2008. But I think, yeah, that is a possibility for sure, because I've seen things in that area.
And this paper was not using deep learning, I suppose.
No. And this the most of the papers that I show, like I show you 3 papers. 2 of them do not really use deep learning. Just there is one paper who used which is deep learning. There are many, just no, don't get me like wrong, but there are many other papers who use deep learning, but I've excluded those as a part of this discussion, because here I just wanted to like start the story of how we can use IMU for detecting human motion and human posture.
Yeah, because I was thinking if you're gonna use deep learning and potentially geometry deep learning, and then Fourier domain is gonna be a nice space to work with compared to the Euclidean space.
Yeah, I think that can definitely be a possibility. For example, I read one. I'll just I'm digressing a bit, but I think it can be of important concept. So I saw this one paper which was using like neural networks, and it was modeling each joint. As for example, if I go back to this particular slide, you can, and I was saying that all these joints can be modeled just by revolute joints. So 2 revolute joints can form a saddle joint, and that neural network was also used some hierarchy. And so, for example, it defined a small couple of neurons for each of the joints, and it was building up the network hierarchically over each of the joints and trying to optimize like the parameters of the pose representation. So I did not go very deep into the math of the paper yet, but I think I have that somewhere, and I can definitely discuss that with you maybe after the meeting or after some time.
Okay, thanks.
All right, but yeah, that's a possibility. I will just take a note of that. Just sorry for the interruption. Thanks for the input, Vani. And yeah, we continue our discussion. Generally, what we are now we have all the things. We can represent our human pose as a vector, and once we have that, we can successfully create our model and incorporate the pose parameters into our model. So the model creation, I will not go very deep into the part because that is not really let's say what I plan to research for now. So in general, and these are mostly standard methods. There are like three general methods of model creation. The first one is geometric primitive, where you represent each human body part as some kind of a geometric to have some kind of geometric shape. So for example, you can represent your limb as cylinders and some certain parts of the body as cones and stuff like that. And then there is a second technique, which is the detailed body scan. There's an expensive technique, but this provides you with much let's say much reliable like post modeling information. So this is detailed body scan, and usually it requires a 3D laser scanner to scan scan the body of an actor and create a rest pose on which you impose the pose parameters, and then you translate the model from the rest pose to identify how the pose parameter changes. And finally, this is another cheaper technique, and it's heavily used in computer vision problems of pose estimation. So we can extract information about the shape of the human body from images directly. So for example, I will see the example next, and we can use all these parameterization to create body models for human. And finally, the part where where all the mathematics and everything we learned where are going to be useful is the optimization. So like any other optimization technique, most of the other optimization techniques, it model the likelihood of the observations for a given configuration of the pose parameters. So the pose that and the pose that best explains the observations is the one that is selected for the final output model. So it minimizes the error. So obviously it minimizes an error function that fits the model data and the given data. So, and the given data can be of two types, as I told you. So we check the model and the model to image association, the error between the model to image association, and minimize that error for optimization. Or we model the IMU and the human model data association, and then minimize the error over that particular domain. So it can be, that's why I called it given data, because it can be image, it can be IMU. So let's just look at an example, because till now I talked mostly about theoretical things, but like just a basic example will bring everything back together. So here we have images of a particular subject, and as I told, like in this part, we can have detailed shape from images. Here, what they do is they extract silhouette, and the silhouette can give us a particular shape of the human. Similarly, what we have is we have a modeling of we have modeled the human pose parameters in a rest pose, and then we tweak the pose parameters to match the silhouette poses, and the one that matches most is selected as the adapted pose for the human. So that is mostly like the optimization technique for a very basic but a very useful optimization technique that we can use for image based pose estimation problems. And coming to the now we will discuss on the selected papers. And the first paper have the image component, because it does from video, it does the pose estimation from video as well as IMU. And this particular this particular technique is called video tracking, and it is taken from the first paper only. So now we have all the things that we need to understand how we can do pose estimation like from a human model or a model based pose estimation. uh, so here, and this is the architecture of the first paper. What they have is multi-view images, which is extracted from 8 cameras, and these 8 cameras are taking videos constantly, and they are divided frame by frame to create the images. We extract the silhouette of the image, and we have a model that we have a model which defines the pose parameters, and how we define the pose parameters is what we have learned so far. And it also synthesizes certain pose, and then we check the consistency of the synthesized silhouettes or the synthesized pose from the model and the silhouette from the original image. And this particular part is called contour consistency. We will see the equation in the next slide. And similarly, the model can also synthesize orientations, because the as we know that there are angles of rotations which define the orientations, and the IMUs that are recorded from the subject also give us the angular orientations of the subject, and we can check for orientation consistency, and we can optimize over this term. What this particular paper do is they optimize over both these terms, which is called hybrid energy, and they say, and they have shown that it provides somewhat better results. I'm sorry, there's someone is drilling my in the next door, if you are hearing the noise. And both these terms can be concatenated together to form the hybrid energy, and the architecture of the paper optimizes the whole model or the whole pose parameters over the hybrid energy term. So if we see this is the energy, so this, if it defines the pose parameterization that we have learned, and it minimizes the distance between the transformed 3D points which comes from the model and the 2D contour points that comes from the silhouette. So this is the minimizing energy term, and the Ni and Mi are something that is defined by a plucker line. Honestly, I really don't have much idea about what a plucker line is, but it is some form of 2D projection. So if anyone has any knowledge on that, it's the best time to tell me, just for my understanding. But generally the idea is the projection of the 2D points from the model and the projection of the 2D points from the silhouette are matched, and then the error is calculated as a sum of least squares, and we minimize this particular error term for the video. And similarly for the orientation consistency, it works as in the same way that I told. The twist parameters of our model is compared with the ground truth orientation of each sensor and the estimated sensor orientation in the tracking procedure, and that is how we define the orientation consistency term, and both of this form the hybrid energy term, and this particular term is minimized for getting the right parameters of the right pose parameters of the model. Sorry, I'll just now coming back to like some of the evaluation measures that they have used. As we can understand that the data set is very rare to occur, because this is first of a kind where no one has yet tried this one before, only with IMU or with IMU and video. So there was no available data set. So the authors of the paper, they recorded a data set with 5 activity sequence like walking, running, and they captured multi-view camera images for all those activities. And they had set 10 sensors. 5 of the sensors they used for tracking, or let's say training the whole system, and 5 sensors for validation. And for the error measure, they used standard techniques. The first one is quite standard. It is the angular error with respect to bone orientations. So for a particular pose, they measured the differences in the angles of the ground truth and what they have modeled, and average over all the angular error. So this is a good measure for orientation consistency, and it is a standard technique for most of the pose estimation problem. Standard technique for pose estimation problem. Another technique that they have defined is called silhouette overlap. So it is how much the projected image and the original image matches. So it's an XOR terms between the image coming from the video and the image coming from the model. And so D is equals to 0 means like it's perfect match, then it's very good, and D equals to 1 means there is no overlap and it's not a very good model. So yeah, sorry.
Can you please go back one slide back?
Yeah,
here. So is there any regularization term here in your loss function?
No, this I don't think there is any regularization term, because if I understood correctly, Ni and Mi is defined as it's called the plucker line. It's it's a method of like converting the from silhouette. It's a method of converting to some kind of 2D projection line, while Mi is the moment and Ni is the coordinate in that projection line. So this is what I understood, and I don't really have like a lot of input on that, to be honest.
Okay, then brings me to the second question. Because you have a heterogeneous input of data, and then do you think from the practical point of view in terms of training, is it easy to impute prior knowledge?
Yes, definitely, and that's what I will talk about, and when later in my when I try to define my research roadmap, because I will probably use prior knowledge for sure as input in my problem statement.
Okay, thanks.
Yeah, so coming back to their to how the system performs. So like the red is just the video tracker and blue is the hybrid tracker. The hybrid tracker means their system with video and IMU, and the red is the system only with video, and they have recorded this for the walking sequence. As we can see, and this is the matching or the overlap of the silhouettes, the this silhouette overlap measure. And as we can see that the red tracker definitely, the hybrid tracker definitely has better like results, because less is better here. And this is the average angular error, and we can see that definitely in the blue tracker, the hybrid tracker, the average angular error is better for frame number 150 to frame number 390 or something like that. So and for the other frames it is close, but still the blue one is better. So overall they have concluded that they have produced a state of the art system with for videos and IMUs. And the good part is that you do not need a lot of video data and you do not need a lot of IMU data, but just like enough, like lesser than the previous like predecessors work, like is just fine. And this particular figure I have just shown because I want to compare it with the next possible set of works. So the average angular error for the hybrid tracker for all the like the sequences is 8.64 for that sensor attached to the thigh, let's say. And I have just used this term because in the next paper I will show you that it's I will see. Anyways, the next, just a brief mention, I wanted to mention this. There was another work which I did not discuss, which was done earlier in 2009, and it measured human pose only from sensor data, only from IMUs. But it was a whole suit that the user need to wear, and it contained like 17 inertial measurement units. So that was very intrusive in nature, and that was coming from a company called XSense, and they have like very strong use cases. They have used it for skydiving, Olympic like runners training and stuff like that. But that was very intrusive, so and it required a lot of complexity and data. So most of the it is also quite cited, but you can see that the intrusive nature of the suit was a reason that most of the people opted for other solutions. And the second paper, it's from the same author, and it's called Sparse Inertial Poser, where they emulate and recovers a full human 3D pose only with IMUs and without any images or video. So the images that you see here are mostly just to denote how the action would look like in a model. The climbing over the wall action would look like over the model, or just doing some random like high, I guess, would look over the model, but it is not used in the actual training procedure. And the sensors in this particular, in the previous work, it measured only orientation, but for this work, they measure both orientation and acceleration. And they use a technique of, of body modeling, which is called SMPL body modeling. And this is one of the most used techniques for without IMU, with IMU data, and no video or image data. This is SMPL body model is one of the most used techniques for pose estimation. So how the thing works is like they have sensors attached to these locations of the human body, and what they do is they also attach these sensors to the virtual SMPL model that they create. And there's a translation between like each of the coordinate system. Like there are a couple of coordinate system for the sensors, there is a coordinate system for the body, and there is a coordinate system for the movement, and there has to be a translation along each of the coordinate system to represent the rigid body motion as we were seeing earlier. And we formulate the kinetic chain as in lines with the SMPL body model, and the SMPL body model has a lot of pose parameters, so it is very difficult. It is computationally very like heavy. But if you but I mean like it's and so we'll see the trade-offs in the last slides. So what happens is, once you have created the SMPL body modeling, you measure the orientation and the acceleration of the actor over the frames, and then we learn the pose parameters for the SMPL body modeling. And as we can see, like it has couple of this represent the pose parameters. The R represents the translation, and then the A represent the R represent the orientations, and the A represent the acceleration. So we have three terms in our like the optimization equation, I would say. The one is with the acceleration, the one that is with the orientation, and finally the pose parameters. So what we do is we try to recover a sequence of poses such that the sensor acceleration matches the corresponding vertex acceleration. This is important to understand. So what is happening is, we have created virtual models, and we have attached sensors to the virtual models, and we have actual actors performing those same tasks just with the sensor, not with video. What we try to see is, when the model does his work and when the actor does the same work, what is the difference, what is the difference in the sensory measurement of acceleration and orientation, and we optimize over those particular terms. And that is how like that is why it does not require any video, because it uses the standard modeling technique to the SMPL modeling technique to create a human model to perform the same things that a video would provide in this particular perspective. And there is another thing, which is they incorporate some anthropometric term, which, and like for example, since it is modeled by a not by an actual actor, but by a body modeling technique. So in that case, to achieve a particular task of running, there can be some unrealistic estimations, like the knee joint can twist like to an extent which does not which cannot happen for a normal actor. So they impose certain limits that for example, the knee joint cannot twist beyond 60 degrees, because that is realistic. So in this way, they incorporate some realism in the body model. And they in the evaluation perspective, we can see that they use the same data set, and they have they compare with like three like benchmarks. I don't know why they did not compare with the previous work. Actually, I know, because this system does not perform better than the previous one, but it does not use the video. So that is what they're trying to push. And since they're trying to push that, they have their what they do is, they compare against the proposed system, the sparse inertial poser, and then they take the acceleration measurement out of it, and they say another system called sparse orientation poser without the acceleration. And then they have another technique, which is called the sparse inertial poser. But if you remember, I talked about a modeling technique which involves like laser scan of the body. And this particular technique is with, and this the final SIP technique is with the laser scan of the body, and this one is without the laser scan of the body. So they have just like created subversions of their own system and compared it against those, probably to prove their like system is better. And as we can see that for all the actions, the SIP performs like better, because it has a less mean angular error. And if you see, I have wait a minute, I will just stop moving the mouse. Yeah, if you see, it measures an angular error of 13.32 degree over all the sequence when the sensor was worn in thigh. And if you remember, like the previous paper, the hybrid tracker was having even a lesser angular error of 8.64 over the thigh over all the actions. So definitely this system is not better in terms of when we evaluate it with the previous system. But the advantage is that we don't need any kind of additional video inputs to the system. So that can be an interesting thing to consider, because in my research problem will not probably have any video. Finally, we have the last of the kind, which is the deep inertial poser. And this one is even like, let's say this one is definitely an upgrade of the previous one. So what they do is, they does not have any actors performing for creating the SMPL body model. They do not incorporate any actors to record the data and to measure the orientations. But what they do is, they consider like previous motion capture data sets, and the pose parameters from those previous motion capture data sets are used to create the body models. And then this put the sensors on these body models and create a lot of synthetic data. And finally, instead, and all these previous methods, both the methods that we have seen previously, they use Newton-Raphson and Levenberg Marquardt algorithm for optimization. And here what they have done is they have used a bidirectional recurrent neural network to optimize the process of predicting the poses, to find the optimal pose parameters for the SMPL body model. So that is what they did different. And the Levenberg Marquardt algorithm or the Newton-Raphson method is an offline computation. The offline computation of the problem, the complexity of the offline computation is very high, and it requires a lot of like computational power, and it takes a lot of time, and that is told by the authors of the paper itself. And here they argue that their system, the training part of their system is it might take time, but once the model is ready, the predictions can be done in real time, and that is why they call it real-time predictor. And they synthesize the IMU data from the motion capture data set, as I have shown in the, here in the image, or as they have shown in the image, to be honest. Yeah. So the main reason that they say that they have used like recurrent neural network is because with the sequence size they can model long range temporal dependencies, which the other authors, the previous works, were failing to address. And that is why they argue that they have better better results compared to the previous works. And they also there is another problem with the acceleration term that is like quite common, that the acceleration term actually fades over like sequences of frames. So for example, if you record frames of videos of like 20 seconds or frames of actions for 20 seconds, then and you have and you for each of the frame, like seconds is actually a big time, let's say like 20 milliseconds. So over like each frame, the acceleration term will be like diminish, and it won't give you like proper results when you try to incorporate it into your model. But they what they do is they try to add another reconstruction in the recurrent neural network, so that the reconstruction of the model tries to reconstruct the acceleration during the training procedure. And they argue that this gives them better like less drift over the acceleration for the subsequent frames. And they have like if we see and if we compare, then we can like, this is the reference or the ground truth. So this is the sparse inertial poser. As you can see that the model that these authors have created is pretty much close to the reference compared to the sparse inertial poser in terms of pose estimation. So yeah, definitely this one is a bit let's say better over their predecessors. Now given that I have kind of tried to look into these three papers at a detailed level to understand what's happening and how what they're working, and these are like the most cited papers in this pose estimation with only IMU data or sparse IMU data. So I have considered this, and now I will try to see what are the like how my research is motivated and how we can explore possible things in my research from this particular domain. So in general, yeah, sorry, yeah.
Can you go back to the last paper figure here?
Yeah.
Here you are training using a deterministic gradient method. And why is that not possible to use a stochastic gradient method?
I don't really know. I mean, this I have not. I think like they have just selected this one. That's why I don't know why. Maybe it's worth exploring definitely if if it gives better results or not.
I'm just thinking if it's even possible, because there should be a good reason for, because they tend to be not good, the deterministic case for.
Okay,
but so maybe it's not possible here. I was just curious.
So if I remember correctly, the authors don't really mention anything about that. I'm just trying to recall things from the paper, like important things from the paper, or at least if they have mentioned, I have probably overlooked. So it can be also a mistake in my part. Maybe I will get back to the paper, and it will be a better way to answer the question.
Okay, thanks. I was just curious.
All right, thank you. Anyway, so in general, the motivation of my problem, the first, so this particular topic probably would consider the next couple of months of my research, and the motivation was to have personalized pose models for athletes, which can give them like a pose estimate in real time, maybe in real time. Also, it can help them to provide a motion estimate, and for example, if a runner is running, how will the running look like when he is getting tired over time? it can help them in technique improvement, and it can also help them analyze their technique better. So this is the application perspective of the motivation of the research. And now I will talk about the research setup, or what we have to address this particular application. We have only accelerometer recordings from mobile and from sensor, and no orientation data, no video data as of now. Apart from that, we can have pressure sensor and heart rate monitor, although I'm not sure whether they're going to be of any use. This data are going to be any use. So what we have right now is accelerometer recordings. And as I have learned from most of the papers, the accelerometer recordings alone are provide not very good result, because they suffer from drift over time. So definitely this is a very super constrained input space, and we need to constrain our output space also in order to formulate a solution. So this is the part that I was talking about, Mavani, if you remember. So I will assume we have knowledge about motion prior. So this prior knowledge is definitely going to be very important for a model, and this can be provided in form of KPIs that we have from some experts about certain procedures of motion, such as running. Then the second part, as we're talking, is we have specific nature of motion. That is, we will consider, let's say, only one form of motion, running or skiing or jumping, I don't know, something like that. And there can be a certain advantage that we can get from this particular consideration, because we can assume the fact, if multiple athletes are running, even though they have different their KPIs will vary for the running, but probably the distribution from which their motion originates have a very high likelihood of remaining together. So that is something probably we can encode in a variational autoencoder or something like that to I don't know, I'm just thinking out loud to incorporate in our research space. And finally, this is the part that Sarunas and I was discussing. We are probably not even required to consider the whole model of the pose as far as the use cases are concerned. We can only consider, let's say, the limbs and the hip while running. That can be enough. So we can constrain our output space also by certain to a certain degree, to address the lack of the data that we have in the input space. So what are the possible areas to explore in this perspective? We can have we can address the spatio-temporal nature of the problem. So these are like very wide areas that I thought form part of the landscape, and each of these can affect the problem of pose estimation in different ways. So we can have a look at each of these components individually, and the Fourier transform, as Vani said, probably could also be a part of this section. So for example, the spatio-temporal nature of the problem, as the time frames, as for example, when you're running, there is a temporal aspect to it, and there is also a spatial aspect to it. And probably during the running, the temporal aspect might play a big role, because running is a periodic motion in nature, and the spatial factor can be subdued in this to answer the particular research question. Definitely, another thing is using deep neural networks in the problem, because although there are works in that, it is still like a big open question whether we can have certain neural networks to address our problem. For example, as I was saying earlier, we can use autoencoder to generate the same motion patterns from similar distribution. And there are a lot of work of pose estimation in terms of computer vision with neural network. We also need to see whether we can extend those works into the section of where we don't have where we only have IMU data, and incorporation of prior knowledge is something that we also need to explore. And also we can see if there are other latent signals that arise from the sensor data, which we can use for addressing our problem. And there are also many physics-based models for human motion which are used in this domain. I've not found many references, but there is one particular book which I was reading, and where it was where there is a section dedicated to this, and there are not many works that are being done in this area. So I think this is also worth exploring in terms of novelty of the research. Finally, if you remember the circles that I created, so the areas in the broad sense that I'm going to affect, In terms of research, is probably computer vision, deep learning, physics, mathematics, and in terms of application, it's mostly being sports and health and well-being. So here in the application part, I am just like right now limited by the RESTFox use case, and but yeah, it can have multiple other use cases which we can see. Now, this is another factor that Saruna says I was discussing. So the collaborative learning, it can be defined as something like, for example, if I am having a model for myself, a personalized model for myself, whether personalized models for many other runners can somehow be shared and collaborated to create, let's say, an extension of um, can lead to a better modeling technique. So this is something which is like, I don't really have any thoughts or sessions on that, but Krister told me that probably we can have a brainstorming session once the previous part is finished. So this is important for the race, like, because we like, we can talk about personalization and collaboration among networks to create better services. So this is something we are definitely going to explore. And finally, the other applications where this can be used is like medical domain. Like, pose estimation is very important for like understanding ambulatory motions of let's say old people who cannot, who are like coming out of injury. It can be used also for gait analysis of runners, whether to better their technique. It can help in injury prevention in medical applications. So Vani is probably is working in one of the use cases of injury prevention, and it might be extended to that as well. And another very important use case is like real-time pose estimates in sports like football, which can help you create better tactics and other important factors. So there is a company which is also our partner called Kinect Analysis, which does something like this. I'm not really sure, but I was just checking out their website once, and I think they have some kind of overlap in this particular domain, which can be useful for me. Finally, for my future works, I plan to explore other kind of data for pose estimation and explore the real-time angle and publish publications. And this time I presented a very broad topic, probably not very like neatly and not in great depth, because I'm trying. This is the first time I'm presenting, and I'm trying to let other fellows know what would be my research work for the next couple of months. But on the next time when I present, I will make sure that I present on individual topics with greater depth, so that I have more inputs on those. With that, I will conclude my presentation, and if I have any questions, then definitely it would be great to ask. Thanks.
Thank you very much for your presentation. So yeah, if anyone has questions, just unmute yourself and ask. So I will start with a question, Deba.
Yeah, sure.
So thinking about possible usages of this pose estimation, do you think it could be used for activities like the kind of rehabilitation gym activities that are used after some big injury that you should do to kind of put your bones and muscles and everything back in to work correctly, where you have like some very specific exercise that you should follow, and it's important to keep your specific
Yeah,
some
definitely.
specific positions.
Definitely, that's a very good use case, and like that is something probably would affect, especially for like the gym exercises, as you said. Vani is also working on something similar, and I guess he is looking more into like the data perspective of it, and how like the data sufficiency works in that domain. But I think once he has something, we can collaborate and discuss on that, because from my understanding, pose estimation has been used, like especially computer vision based pose estimation has definitely been used in this domain for understanding ambulatory perspective of old people, as I was saying, and also athletes who are coming back from like rehabilitation to test their pose and everything, whether they're fit to come back into the sports or not. There are like applications of computer vision based pose estimation definitely in this domain. So so if there is application in the computer vision based part, then definitely we can absolutely have something in the IMU best pose estimation, because the end result is just detecting poses, which is just the data part. The source data differs in this case.
Okay, thank you.
Yeah, thanks.
I think I wanted to add something for Ludovico, is that once we have pose estimation for the human body, you can do many more things. You can measure like distances, and you can measure a lot of activities without any uncertainty, because it's easy to track things once you have like key points. I don't know if that makes sense.
Yes.
Yeah. This actually leads me to my next question, which would be, once you have pose estimation working, so let's say, I mean, I know your area is mostly on getting the pose estimation, but once you get it, how can you use it, for example, in machine learning? So at a practical level, how can I use a pose estimation to do, I don't know, either to understand the evolution of poses or to compare the poses of different people, so or to fit it in a machine learning system? So what kind of machine readable data do I have after I do pose estimation? So how would you pass that to downstream tasks?
Okay, so in that case, so once you have like the output, you have the data that you have is just a vector of the pose. So I guess that can be, let me just think of if there is any other.
I think, can I step in?
Yeah, sure. If you have
I think if I think about it, it's like if you're running and you're not having a good style, and we have your pose, we can have a better style recommended for you, and we can show you in terms of poses how you should properly run, given your input, like heights and stuff like that.
Also, so for example, another thing that I was like thinking about. So if you see what for example, while you're running, you have certain KPIs. I don't know if you've seen the Resbox app, but there is ground contact time and what is the frequency for running and stuff like that. So these KPIs are specific to person. So once we can try to relate the poses to the KPIs, and we can try to let's say ask you that your ground contact time is high when you're in this particular pose, but maybe if you go to this pose, your ground contact time will be lower, and you will be running better, and you can improve your technique to injury prevention and stuff like that. So these are very like specific applications I can also I can think of in this domain, in this area.
Okay, thank you. Are there any other questions? Then, if there are no more questions, I think we can say thank you to Deba for his very good and very nice presentation.
Thank you.
And yeah, I guess see you all I think in 2 weeks to avoid Easter.